do that.
So now we're going to talk.
We can solve this equation by observing that the A plus B
EFT is an algorithm,
right? Because they're is equal to minus KAB plus KAB.
We've already met this before.
So this is 0.
So we're just going to
A plus B
a
is
little
a
bit more in detail about how it works.
So we can go A plus B is equal to whatever we started.
Let's look at this. Let's imagine
we know once, so we can substitute that.
If we do any numerical solution, we really have a finite periodic domain.
Is equal to minus K.
Follow the notes. So if we're going to do it numerically, even if we want to go from minus infinity to infinity, we're going to have to go from minus L to L. We can't get to infinity, right?
Is equal to minus KAB. Sorry, plus KAB.
So we obviously, if you want to go to infinity,
A
make
is
it back,
equal to
whatever
B
that
minus
means.
that.
So we've got C of we do a Fourier series here on the solution on this finite interval.
So it's K
times
A,
the coefficient,
which is
e to the I K
A naught plus B naught minus B.
I'm just using K in here, but
so this is like a
I in over L. This is just a standard Fourier series, just a complex equation. You normally would see them as sines and cosines, but actually it's always better to do the complex one.
Solve using separation of variables.
FFT and everything's based on that. Okay, so we use
one of the
this is just a normal Fourier series, and it goes from
your
minus
problems in the assignment.
So we can represent a complex function.
Okay, the note solution's given here.
Okay,
so that's no problem.
Real, then these will have some.
This is just a, you can do this by separating it, taking it out here, and it's like if you look at it on a phase line, you've got equilibrium points when B is 0 and when B is this starting point.
That tells us immediately
the amount that you started out at the end. Okay. So yeah, here's the phase. Okay. And then up here is a bit silly because one of the chemical species become negative, but the equation flows like that into this equilibrium.
Infinity of
all right.
d by dt of c in hat e to the I k in x must be equal to the sum from n equals minus infinity to infinity of minus kn squared c in hat of t e to the I k in x. And then of course that means that each of these dt c in hat is equal to minus kn squared c in hat. You go from the orthogonality of this for a series, so we get c in hat is equal to c in hat at naught, and this is a function of time, e to the minus k squared. So I've forgotten my d here, haven't I? Given to minus kn squared dt. Okay, so therefore we've got this expression for the solution. E to the minus kn squared td times e to the I kn x. So that's the solution to the equation. So now we've got to try and solve this numerically, right? We're going to try and do this integration. And we also know that we can calculate what C in naught is as well from the Fourier series. Let me just write that down here. So C in hat naught is the integral of, from minus infinity to infinity, minus L to L, e to the minus I kn x times c naught of x dx. So there's our formula here. So this is the solution to this equation, right? Written down. This is just separation of variables for the heat equation, basically, and nothing more than that. So this is the expression you get. Assuming that the solution, all I've done is assume the solution is periodic, which is the boundary conditions to imply if you want to try and model it, something that's infinite. Okay, we don't want to have any effects from the wall. So what we've got, we've got a process here. We take the initial condition, we integrate to get these C and naughts, we advance them and take them back. So in that, we just want to show you how each of these steps, this step here is equivalent to a fast Fourier transform, and this step's equivalent to an inverse fast Fourier transform. So I need to show you that.